everyone. We're going to start now. Some more people may come in, but they're just coming in quietly. So welcome to this talk, which is now our regular monthly talks at Battersea Arts Centre. Just quick housekeeping, toilets outside, women's on the left, and then the other side of the staircase of the men's. Fire exit is just the door you all came in. Just to say that we will be filming this, so if anybody's unhappy with it, I don't think the camera's going to be on anybody except facing this way anyway, but just to let you know, that's not a problem. We all know the Arctic is warming much faster than other regions of the world, and the sea ice is melting. And if this melt is left unaddressed, we risk a blue ocean event in which Arctic sea ice disappears entirely. And this will be a tipping point with catastrophic consequences. So can we do anything about it? I'd like to introduce Andrea Ceccolini, who is co-CEO of Real Ice, a UK startup that's researching the preservation of Arctic sea ice. And also here is Simon Woods, Executive Chairman and co-founder of Real Ice. So Andrea's going to talk about Real Ice's work on ice thickening, which encourages the natural process of Arctic sea ice generation. And the talk will last around 40 minutes, and then we'll have a Q&A, where we will have the opportunity to ask Andrea some questions about their work and perhaps also on some broader themes around, in scare quotes, geoengineering. I know this is a controversial term. So over to you, Andrea. Can we save the Arctic sea ice?
Thank you very much. Thanks for the introduction. So, hello everyone. I'll tell you a story about the Arctic, but before, let's go to basics for a moment. We all know what global warming is. Can we find a definition which is related to the energy balance of the planet? I think this will be useful as we go on and we discuss how important the Arctic sea ice is for this energy balance. So global warming, in simple terms, is about the difference in energy that we receive from the sun, from solar radiation, and the energy that the planet reflects back to space or radiates back to space. Two ways to release the energy. This difference is what causes the planet to warm up. We've been in a balance for thousands of years, but in recent times the balance has shifted. You know why? Greenhouse gases are one of the main culprits, because the planet tries to radiate energy back to space, and some of that, too much of that, is trapped in the atmosphere, to make it short. So that's important. So why is this relevant for the Arctic sea ice? Because that's a vast area and it's very bright, and it's one of the main contributors to this important sort of reflectivity of the planet. So we receive a lot of solar energy in the summer. In the Arctic summer, we reflect up to 90% of that energy back to space. If we lose that ice, 90% of that energy will actually be absorbed by the ocean. So that's the difference between having ice and not having ice in the Arctic region. One might say, is the Arctic, so important? Why aren't other regions that important? But this bright surface is quite rare. The other region that has a similar sort of brightness is Antarctica. A very different problem. We know the glaciers there are an issue, shifting into the sea, creating sea level rise. But we know for thousands of years it's going to remain bright and white, because it's a landmass with very, very thick ice on top of that. So big issues, but of a different type. In the Arctic, that's an ocean. In the ocean, can lose the ice. The ice is only 1, 2, 3 meters. When it's gone, you have the blue ocean under that. So it's it's something that is happening right now. And in fact, if we look at the trend, we can look at two things. On the right side, this is the area covered by the sea ice at the summer minimum. Pretty much now, mid-September every year, the ice retreats to a small area, which in recent times has been very, very small, around 4 million square kilometers. We lost nearly half of that area over the past 40 years, since we started to observe it with satellites. So we have very accurate measurements. But more importantly, this is the left diagram. It's a spiral going down very quickly. Look at the black line there, which represents September, so the summer minimum. We've actually lost 75% of the volume of that ice. So it's not only reducing in area, it's reducing in thickness. So when we get to the end of the summer, in September now, we don't only have a very small area, we have a very thin ice. If you look at the extrapolation there, the sort of the little lines, all predictions are telling us that within the next 10 to 15 years, we are likely to see the first blue ocean event, which means at the end of the summer, we will have virtually no sea ice in the Arctic for the first time in 1 million years. So it's not like something which the planet saw, 10,000, 20,000, 1 million years ago. We might, before the last big ice age, we might have had something like that, but this has been a long, long era of sort of frozen Arctic under all conditions, and we've been able to change that, unfortunately. So a few numbers here, and a couple more tipping points, because the Arctic has not only the sea ice problem, as it was said in the introduction, the area also, thanks to this spiral and this feedback loop, is warming up much more quickly than the rest of the world. So there's two other very important tipping points which are important at global level. One is the thawing permafrost. So the whole Arctic land, but also the bottom of the ocean, has a very thick layer of permafrost, which includes a vast amount of methane. So if you thaw the permafrost, you release vast quantities of methane, which could hamper all our efforts to do decarbonization, would be lost, because that's obviously an incredibly powerful greenhouse gas. And then at the same time, we have Greenland, which includes in its sort of glaciers up to 6 meters of sea level rise. So if we lost all the glaciers in Greenland, we would get 6 meters sea level rise all over the globe. This is not something that is going to happen over decades, it's a much longer period. But if we accelerate the melting of Greenland, we will see the sea levels come up much more quickly than predicted and modeled. So warming up the Arctic, losing the sea ice, is going to create an acceleration for these two other tipping points. So this is why we need to preserve the sea ice as much as possible. Where is the Arctic? They don't teach us much about the Arctic in our world. We look at maps like these and people think it's a little blue strip at the top. Greenland is a massive, almost a continent there. It's not the way one would see that from the top of the globe. It's a large ocean, as we said. It's actually twice the area of the United States. So this is why we can play with an incredibly powerful resource there. When it's full of sea ice, it's bright, it reflects a lot of energy back to space. It's massive. I want to show you a video from NASA. So you get an idea of what has been happening in recent times.
In 1978, satellites began continuously observing the polar regions, and the dynamic beauty of the Arctic sea ice was revealed. What we expect to be a solid mass of ice is actually in constant motion. As researchers continue to seek a deeper understanding of this region, new information about how sea ice changes is coming to light.
In this animation, we're taking Arctic sea ice into the third dimension. Here, we're looking at the ice age, which is an indicator of thickness. Generally, older ice is thicker ice.
That's the voice of Dr. Walt Meyer, Senior Research Scientist at the National Snow and Ice Data Center.
What you see in this animation is the ice pulsing out and in with the seasons. In winter, the ice grows out and expands outward. In summer, it contracts inward as it melts. You see the whiter ice, which is the older ice, moving around the Arctic, being pushed around by winds and currents that move the ice. Over the years, the ice pulses around, it moves around towards the top along the coast of Greenland. The older ice eventually moves out of the Arctic and into the North Atlantic, where it melts. The ice gets replenished within the Arctic because some of the ice survives each summer and grows older. And particularly in a region north of Alaska called the Beaufort Sea, where the ice spins around in a clockwise direction called the Beaufort Gyre. And that ice can keep spinning around oftentimes for several years and gradually getting older and thus getting thicker. Eventually, the ice will spin out of that gyre and go out through Fram Strait. In the past, we've always had enough ice growth and ice aging, enough ice surviving the summers to replenish the older ice that's lost. But in recent years, we've seen less replenishment. There's been more melt during the summer, so the ice that goes out through Fram Strait has not been compensated by the ice growth. In addition, especially in recent years, we've seen some pretty remarkable things in the Beaufort Sea, where that area that used to be a nursery for the development of the older ice allowed the young ice to age and mature. What we've seen instead is the ice is now more broken up, more scattered, and that's allowing the older ice to melt within the Beaufort Sea. So we're seeing the Beaufort Sea go from a nursery to a graveyard for older ice. As we get towards the more recent years, much of that oldest ice, the ice that's older than 5 years old in the bright white, has almost virtually disappeared from the Arctic Ocean. And the Arctic is now dominated by younger and thinner ice.
Massive difference. In only 40 years. This was, pretty much the same a million years ago than what we had in the 70s, then in recent years we're losing everything. So this is why we get the Arctic amplification, because we're losing all that sea ice, so that the Arctic gets warmer, the warmer it gets, the more sea ice we lose. There's this feedback loop, unfortunately. Let me go back to the slideshow. So, and it's not only about climate. So let's look a little bit more in depth about the Arctic and what we find in there. There's 500,000 indigenous people still in the Arctic. I think the Western world has done everything to decimate them, but there's still Inuit population, in particular Northern Canada and Alaska, where we've been sort of visiting for our work, and they, to a certain extent, still live in their traditional, with their traditional culture, which in particular has a sort of meat and fish only diet, which is very weird for the rest of the world. They, when you look at reindeer in the Nordic countries in Europe, caribou is pretty much the same animal in Northern America. They say harvesting, by the way, when they talk about hunting, just to give you an idea. Even when they talk about sort of sea mammals, their life, the life of these populations also depends on sea ice. Might sound strange, but with no sea ice, they cannot hunt, they cannot fish, they cannot move across communities. It's impossible, given the land features, to move even with a snowmobile across land easily. So when they travel across communities, they typically do it across the sea, which is much, much easier for them. So this is changing everything for these people. Having 1, 2, 3, 4 months of no ice or unstable ice during the summer or the shoulder season, so beginning of winter, beginning of summer, it becomes uncertain. Can we go out? Can we travel? Can we go hunting? Fishing means a lot to these people because they cannot draw from their typical sorts of food. We've been, so I put another picture there because things have been changing for a while. This is Cambridge Bay, it's the Canadian High Arctic Research Station. This is what we used last winter, for our research in the Arctic. And there's a good reason why Canada would establish a center like that, 70-degree latitude, far from everything, because there's an increasing amount of research that is being done in the area. More and more researchers want to know about the trends and what to do to save the Arctic. First of all, measure, try and understand the phenomena around the loss of sea ice, but also, like us, try to do something about that. So there's more about the Arctic that affects us directly. The changes that we've seen in the Arctic are causing changes globally to the climate. One of the most important changes that we see on a regular basis at our latitude is that the jet streams, which are typically quite regular at a given latitude and separate the cold atmosphere of the Arctic from the more moderate atmosphere of lower latitudes, they are being disrupted by these changes in the Arctic, and they cause extreme events. So very, very cold at lower latitudes, or 20, 30 degrees at the North Pole, something that wasn't experienced before. So there's a disruption of that. Those jet streams, I think a moment ago someone was talking about the hammock. That's something also that is being disrupted by the changes in the Arctic. The loss of sea ice means that the salinity of the water, which goes deep into the Arctic in the north and then travels all the way to the south of the planet and comes back up as a warm sort of stream that keeps Northern Europe warm. And this country in particular is also being disrupted and is getting weaker. So there's a lot of studies on trying to predict whether there's going to be a collapse or not over the next few decades. Not an easy one at all. We are seeing changes which are of global nature, again with a root cause in the Arctic itself. I think we can skip this, but just to say this was just a little someday when we did this presentation at the school. It's just to say we're going to regions which are nearly deserts. I mean, the Victoria Island, which is where Cambridge Bay is, where we went to do our test this last winter, is as large as England, with only 1,900 inhabitants, most of them in that village, 1750, mostly Inuit. And it's part of a region in Canada called Nunavut, which is over 2 million square kilometers and only has 39,000 inhabitants. So we're talking about vast, regions with very little population, but so much, such an importance in terms of global climate. Just to mention that in 2023, instead, we went to Nome, Alaska, to perform similar tests, and those were our first field trip. Then we decided to move to Cambridge Bay because, again, Alaska has been sort of low on sea ice, and now we get reliable sea ice only in January and February, basically, in the Bering Strait, when they used to have maybe 8-9 months. Where in Cambridge Bay, we find a bit more reliable sea ice. And yet again, we had to go in November 2023 for our 5th trip, and sort of last minute, the polar station called us and said, it's too warm. We are like 5-6 degrees higher temperature than ever recorded for October, and there's no sea ice at all. The rivers are not frozen, the lakes are not frozen, something unprecedented, so don't come because it's totally unsafe, so we have to go in January instead. So things are changing quite rapidly. So we can do something about that. There's been science and literature for around 10 years on how we could actually address saving the sea ice and also trying to figure out a possible engineered solution to do that. So the one we are researching is called ice thickening. So it's very simple, and it's actually something that people, for various reasons, have been doing for much longer. And it is about pumping seawater on top of existing ice to create additional freeze at the top. So imagine you are in winter, it's cold, the sea ice has started to form. Like every winter, at some point it will start to freeze again. The ice is a good insulator. So if you look at the first picture, and the snow on top is an even better insulator. So when you start to have a bit of ice with a bit of snow on top, basically the growth stops or goes very, very slowly because of the insulation between the cold air and the water. The bottom of the ice is where the ice actually continues to grow. The normal accretion is at the bottom, in the interface between the seawater and the ice itself. But because it's thick and it's far from the cold air, it stops growing. By pumping the water on top of that layer of snow and on top of the ice, we put liquid water in contact with the cold air, and that freezes immediately. Within hours, you have an extra layer of sea ice. So that's easy. People have been doing it to strengthen ice rinks, ice roads, lakes. In winter, now they have some ice, they want to do some activity in a lake, even in the Nordic countries, they do exactly the same. They pump some water on top of the existing ice, it gets thicker and it's more stable, more safer. So clearly the problem is doing it at a large enough scale, but also do it in a way that we know is going to create the gain we want. What do we want? We want that ice to survive longer in the following summer. Because if it survives longer during the summer, when we have the daylight again, it will reflect a lot of that solar radiation back to space. So that's the main sort of climate objective that we want to achieve. And interestingly, we discovered, also thanks to one of these research papers from the University of Washington, that just simply by flooding the snow layer, so removing the snow, which is the most important insulator, and basically freezing that layer, we reduce the insulation so much that you can just leave the ice do its job on its own naturally for the rest of the winter, and we see much more increased growth from the bottom as well, exactly because we remove that type of insulation. We don't need to even pump so much water. Imagine the snow will be 15, 20 centimeters when we intervene, and we freeze that layer, and then with 20 at the top, we obtain 70 extra in total at the end of the winter. So that's the type of gain that the modeling and the lab tests indicate. So this is a picture from our Cambridge intervention. You see making a hole in the ice. Here we had about 1 meter 20, 1 meter 25 of sea ice in total, just making like a half a meter hole to see how the new ice was. You see it's got a slightly different color because it's a mix of snow and water, and this is the pre-existing ice, which is darker because it's like, if you take it out of the water, it's like glass, effectively, not the pure ice that you build with water. When you do it by mixing it with water, you also take a little bit of air, so it becomes a little bit lighter. Interestingly, because you're pumping seawater, This top layer at the start is also a bit more salty than the layer at the bottom. This was one of the issues which we wanted to validate with our intervention, because if you leave a lot of salt on top of the existing ice, there's a chance that it's a little bit more brittle. When we went back in May to check, all that salt had drained back into the sea. So that was basically fresh water, only 5 parts per thousand of salt. The Inuit use it to actually drink. So it's a source of water for them, this ice, so it's nearly fresh water. Like the layer at the bottom. So this is, so it's really simple, the test. Make a hole in the ice, put a submersible pump into the water, pump water for as much energy as you have. It will flood the snow, will be driven by the snow itself. So if there's a lot of snow, it will move out slowly. If there's only a thin layer of snow, it will spread a bit more quickly. When you've done that, you wait for a few hours, depending on the thickness, it will freeze, it will be your new ice. So it has more chances to survive in the following summer. We did the same in Cambridge Bay, but on a larger area. We covered, if you want, the area of a football pitch, roughly, for about 25 centimeters of thickness. So we created roughly 1,000 tons of new ice while we were there. And then, as I said, when we went in May, there were an extra 25 also at the bottom. So all in all, we had half a meter of extra thickness gained just by doing, a few days of pumping, like 2-3 hours a day, effectively, of tests. I want to show you a little video of our trip in Cambridge Bay, so you get an idea of let me see. This for a moment. We are in the charts in the polar station, assembling sort of power station. Then we need to carry all the equipment out at sea. We were about 5 kilometers out from the village. This is just in front of the polar station. We are carried with box sleds, which the Inuit use to carry animals when they go hunting. This is the location where we did our intervention. Nearly midday, as you see from the sun, high up in the sky, snowmobile. That was our camp during those 2 weeks. You see that the weather is not always great. So this is just showing, this has been re-iced already. We show what I was showing earlier, just a hole to see the layers and the stack of new ice. It's just the pump starting. We're pumping roughly 1,000 liters per minute, so it's a small power, 600 watts, a quarter of your toaster, but quite powerful in terms of flow. It's a very efficient job. If you measure the amount of energy we use to re-ice versus the energy that we push back to space, there's a ratio of 30,000. Every kilowatt hour we use to pump water, we reflect back 30,000 kilowatt hours of energy back to space. That's the ratio. And we create some nice ice as well. We see those crystals where it's humid and very cold. This is when we measure the thickness with a smaller type of grain. So that's to give you an idea of what we do when we go out to the Arctic. We do many other things as well. If you look at this picture, we were giving a demonstration just in front of the village to a local school. So this was a middle school coming to the sea ice with us in minus 35 degrees, so kids were still allowed out. And yeah, we had a great reception. We presented to local Inuit organizations, to the personnel of the polar station, to the school, to other groups locally, and generally been well received as a positive message. Can we do something about that? And we listened to many, many stories about the importance of the ice for their culture, and how the elders that were the ones to determine when certain things could and should be done. We go hunting, we go meet, the people from the next village 500 kilometers away, or whatever they had to do was based on these cycles of ice, and now they can't predict anything anymore. So you can imagine the society is shifting very, very quickly. There's a huge amount of issues with the youth losing, if you want, touch from their original culture. So it's there's a lot of there's more social scientists, they say, than Inuit now studying how things are going, but it's not a joke. It's pretty dramatic for them. So how do we scale something like that? And it's all easy, make a hole, pump some water. To make any difference from a climate perspective, we need to cover something like 1 million square kilometers. That's actually what we calculated that would be enough to preserve the sea ice that we still have at the end of the summer, and also roll back a little bit to what we used to have maybe 10, 20 years ago. So can we send, a lot of people out with pumps, making holes? It's just impossible. In the harsh climate means you can't really operate. It's not just about the people in pain with minus 50 and strong winds, and obviously you need to go far away from communities. It's that even the machines don't survive in that weather. So how do we scale it? Our idea has been to build an automated solution based on underwater drones. So make intelligent small machines that carry a water pump and enough energy. They move to the target area, make a hole in the ice from under the ice instead of making it from the top. So they're always in a protected environment, because the water has a constant temperature, just above freezing, minus 1.5 degree. You can move with low energy underwater. There's no winds, there's no, on top the ice breaks, the ice has ridges. If you've seen these movies of the explorers going to the North Pole, every now and then they need to take their sled on their shoulders and climb, maybe 4 or 5 meter walls. If you go underwater, there's none of that. You can move in 3 dimensions, find the right spot, make a hole, pump, visually see how far you pumped, how the water moved, how you re-iced. You go back to base, download the data so the base knows where to go next with the next drone. And so you build an automated solution that can scale to a large area and only needs operations in a sort of centralized way within energy hubs or within small bases that provide the energy for the drones to operate. So this is our idea. What would it look like? This is just an example. Just imagine, maybe a 2 meter type drone. We need something to make a hole in the ice. Our idea is that probably the best way is using thermal energy. So it's like a hot pipe. So when we come close to the ice, like a periscope, it goes high, it goes through the ice, and then it's also the output pipe of the pump. We can pump the water, again, take it down and go back to base where required. This is technology of 50 years ago. That's the other thing which we wanted in our project. We don't need drones that go 3,000 meters underwater like they're doing now. If you look at drones that operate on underwater cables or pipelines, they have robotic arms. They can take samples of things, fix objects. We need to stay 5 meters underwater, no more than that. It's simple. We don't need a massive amount of energy to do the job. The only thing that hasn't been proven is making this hole from under the ice, which is something which we are studying now as a project with a university to see how to best model that. So a few numbers. They look large, but we'll talk about other numbers in a moment, and you tell me what is larger. So yeah, 1 million square kilometers, this would be full scale in a number of years. Potentially 500,000 of those drones. To give an idea, each of those drones, in terms of technology, is like an e-bike. It's more of an e-bike than an electric vehicle. So in Europe alone, we produce 5 million e-bikes every year. So we're not talking about numbers. Europe, we produce 70 million cars every year globally. It's a bad thing, but it's 70 million. Here we need 500,000 over the course of the project to scale to where we want to be. And it's simple devices. Energy hubs to distribute energy. We want to do it in a zero emission way. So all renewable energy using green hydrogen. So it can actually, that renewable energy can be stored and can be delivered to the devices when we need it in the winter. And this would be like a small industry. Instead of drilling oil in the Arctic, which they're doing, we want people to make ice, which is first and foremost an exercise of ecosystem preservation. This is what it is, first of all. Then we know that that ecosystem is important for climate because of the reflectivity of the sea ice. But it's also something that we want to save, like a forest or a coral reef that's been there for a long time, and we need to make sure we help nature do its job a little bit better. Yes, we use technology, there's that bad term that people want to use to classify these type of projects, but every solution, and we need many solutions for climate, will need technology because we need solutions that scale, and with nature-based solutions, the ones that don't need any type of technology are not moving quickly enough for the problems that we are facing, and all others, even planting trees, are technology intensive now, let's be honest. We're not going out with a stick to plant seeds if we want to plant 1 trillion trees. These are the numbers we're talking about. We work with Cambridge University. They are supporting us in this research exercise. Don't forget, this is still a research exercise. We want to learn, we want to advance our knowledge. Can this be a solution for our planet? Can this be a solution for whoever decides, the United Nations, the Arctic Council, etc. They're supporting us. Their director, Sean Fitzgerald, likes to say that this type of research costs millions, so it's not like peanuts. It costs millions to study. It might cost billions, as you see, to deploy, but they save trillions in avoided damages. And I mean, the best predictions we have now, we're probably up to date with all of that, is that by 2050, the cost of climate-related damage will reach 20% of the global GDP. We're talking about over $20 trillion a year in climate damage. So we're talking about orders of magnitude. Any fraction of a degree that we can cool the planet and avoid some of those effects can have an exponential return in terms of avoiding all that pain. It's not just about money, it's about the pain. Single events now, the last floods in Central Europe, 5 billion euros. Wildfire in Canada, tens of billions of dollars. 2 years of wildfire in California, $100 billion. Single events or a single season of one of these climate risks is a multiple of what we would need over, like 10 years to try and save these resources. So we need to consider that. Last point I want to make is we all know that the solution to the climate crisis is to reduce the concentration of greenhouse gases in the atmosphere. So we passed 420 CO2 part per million. We need to go back to whatever, 300, 350, whatever is considered a safe level. To get there, we need decarbonization, to get to net zero first. If we get to net zero, and at that time we have 500 concentration in the atmosphere, what does it take to go back to 300, 350? It's generations of carbon capture technologies that we still don't have. So we need to cool the planet as well while we do all that. It's not a question of either or, the moral hazard question, can we wait, incentives here and there. We are at a stage probably 20, 30 years late for those conversations. We need to do some of this as well. Obviously, what is safest and what is most effective. This is why we need to push research to a point where we give enough information to whoever wants to implement these solutions in the future. And I would stop here because I've gone past.
Thank you so much, Andrea. That was absolutely fantastic. I'm sure people have lots of questions. I don't expect you need me to field them for you. You can see people. Can I just start asking one? Are you, from your research, ready? And if somebody handed you $50 billion, are you confident this is going to work? And are you ready to go? What's the timescale?
So, no, this is why we are going to do these tests. And we have a program of, over the next 3 winters, we want to do more testing for 2 reasons. One is testing the effectiveness of the method. We're relatively confident there. It's about optimizing energy, deployment, etc. We know that there would be some results. So how much energy do we want to put? How much engineering do we need to deploy? That's parameters that we still need to learn. But the other important aspect is it safe? We need to do a full impact assessment, if we want to be honest, because it's not just us and the ice. There's wildlife, indigenous population, there's an environment there that we need to make sure we're not disrupting it in any way which is comparable to the disruption that it's getting anyway. Here we're talking about the total collapse of the Arctic ecosystem. That's what we are facing. The sea ice, one point I didn't describe earlier, is the starting point of the food chain for the whole Arctic biodiversity. So those micro plants that grow under the ice, macroalgae, etc., feed fish, sea and land mammals in a way or another. So it feeds the whole ecosystem. Losing the sea ice is not just the polar bear that cannot rest or the seal that cannot, put the babies there. It's food not available for them, for the whole wildlife. So we need to compare it with that. But obviously we don't want to make any damage even close to that. And we need to do analysis for that. So an impact assessment will also be run as we go on with the test. In parallel, we're prototyping that engineering to make sure that that technology can actually be deployed, because it needs to be solid, stable, efficient, use as little energy as possible, not pollute. So there's a number of things that need to be done anyway. So we wouldn't be able to use 50 billion tomorrow, but we know that if we had more funds, we could speed it up a little bit. But we need, in any case, there's a time of policy makers that we cannot compress. We need to convince a number of institutions at national and supranational level. This doesn't happen overnight. So we need to do a series of more and more convincing tests to get to that type of conversation.
Okay. So, do other people have questions? And so at the back there, just
Hi, that was really fascinating. Thank you. I've learned so much. I just wondered, other than the budget, and you mentioned sort of like policymakers and testing, what sort of like the other biggest barriers to this sort of becoming a reality?
But one is certainly the sort of very tough conditions we face in the region to do any test. The logistics is incredibly complex, and I'll ask Simon to also maybe answer this from their perspective. But it's very difficult to even just go there and carry a little bit of equipment, find the necessary energy, move to the sea ice. It's an environment where only very few humans trained that have been there for generations can operate safely. We are completely out of safety environment when we get there. We need guides, Inuit guides with us all the time, so this is also what slows us down. And we can only test in the winters. These lab tests are no longer representative. They're important on the microstructures. How is it best to grow ice at the micro level? But if we want to see the effect, will this survive over the next summer, we need to do it on a bigger scale. So starting from this coming winter, we will try and cover up to 1 square kilometer. We went through all the permitting steps, so from the Nunavut sort of federal, if you want, a regional level down to the village, hunters and trappers that can comment on what we do near their village, and we have the permit to do that work. We identified the area 7 kilometers from the village, etc. But you need, large enough to do it, and it's difficult. So that's definitely one of the complexities. I'm sure that.
I think possibly the health barrier is just the idea was totally new. People are used to the idea of preserving the rainforest. You have the Amazon Fund that's been set up in Brazil, proposing to make that much, much larger. So people are used to the idea of preserving other ecosystems because you can access them, people have seen them. The Arctic, very few people have been, and even researchers who spent their whole lives in polar environments, we saw some at Fairbanks University who said, well, there's nothing we can do. And so getting over that hurdle to, well, actually that's maybe not the case. More research required, but maybe we can do something about this ecosystem. It's not Greenland where you have to operate on these enormous thick glaciers, or Antarctica, which is impossible to get to, and again. This is, as Andrea said, this is a problem space where the ice is not so thick, and we can make quite a bit of difference with a very low energy solution. So getting that out, having people kind of get used to that idea, and then marshalling all the stakeholders to start working on it at scale.
So, Glenn and then Glenn, do you want to?
I was wondering, this is absolutely fascinating. I was wondering if you'd had any reaction from fossil fuel companies at all. Because they have been known to be sort of slightly aggressive, I suppose you could say. Have they been a problem, or have they not said anything at all about this?
We haven't had direct interaction. Nobody's come to us to say do, don't do, or anything like that. We know they are very powerful in the region. We went to Nome, and there's one of the major, oil producer that is sponsoring everything from, local park to whatever, playground with their name, and obviously they